Welcome back to our tech podcast, where we delve into the intriguing world of database systems and their complexities. Today, we're focusing on a vital concept in modern data management, leaderless replication. This approach allows multiple clients to write to a database at the same time, ensuring that no data is lost even when operations overlap. We'll break it down with a simple example and explore the implications of concurrency in data operations. So, grab your headphones and let's dive in. To illustrate leaderless replication, let's consider a straightforward scenario involving two clients adding items to a shopping cart. Initially, the cart is empty, but both clients are eager to add their selections, leading to a series of writes to the database. First, Client 1 adds milk to the cart. Since it's the first write for that item, the server successfully stores it and assigns it version 1. This versioning is key because it helps track changes over time. Next, Client 2 adds eggs, completely unaware that Client 1 has already added milk. The server assigns this write, version 2, and stores both items separately. This is where we start to see concurrency come into play. Now, Client 1 wants to add flour. It sends the server the value it believes the cart contains, which is just milk. The server recognizes that this write supersedes the previous version of milk, but is concurrent with the eggs added by Client 2. It assigns version 3 to this new cart state, while retaining the eggs. Meanwhile, Client 2 is still active and wants to add ham to the cart. After merging the values it received from the server, Client 2 sends a new cart state that includes eggs, milk, and ham. The server processes this as version 4, keeping all the concurrent values intact. Finally, Client 1 decides to add bacon. It merges the current values from the server and sends the updated cart. The server recognizes this new state as concurrent with the previous updates, ensuring that no data is lost. This example shows how concurrent operations can lead to multiple versions of data existing simultaneously, often referred to as siblings. The server must keep track of these versions to maintain data integrity. So, how does this all work behind the scenes? The server maintains a version number for each key, incrementing it with every write. When a client reads a key, it receives all values that haven't been overwritten, along with the latest version number. This is crucial because it ensures that clients are aware of the current state before they write back to the server. When clients do write back, they need to include the version number from their last read. This helps the server determine which values can be overwritten and which must be kept as siblings. If a write doesn't include a version number, it's treated as concurrent with existing writes, safeguarding against data loss. An important aspect of this system is how deletions are managed. Instead of simply removing an item from the database, a deletion marker, known as a tombstone, is left behind. This prevents issues that could arise if an item is removed in one sibling but still exists in another. As we transition from a single replica to multiple replicas in a leaderless setup, the complexity increases. Each replica has to maintain its own version numbers, which creates what's known as a version vector. This vector keeps track of the versions seen from other replicas, helping the system distinguish between overwrites and concurrent writes. When a client reads from one replica and writes back to another, siblings can be created. However, as long as the merging process is handled correctly, no data will be lost. The version vector plays a crucial role in managing these complexities effectively. Now, let's take a moment to consider the broader implications of replication. Replication serves several key purposes. It keeps systems running even when machines fail, allows applications to function during network interruptions, and handles higher read volumes by distributing requests across replicas. However, it also presents challenges that require careful consideration of concurrency and fault tolerance. For example, if a leader fails in a single leader replication model, There's a risk of losing data if an asynchronously updated follower is promoted to leader. We also touched on consistency models, which guide how applications behave under replication lag. Users should always see the data they submitted and shouldn't encounter older versions of data after seeing a newer one. These principles help maintain a reliable user experience. In conclusion, leaderless replication is a powerful strategy that enables concurrent writes in a distributed database environment. By leveraging versioning and version vectors, systems can effectively manage data integrity and ensure that no writes are lost, even amidst concurrent operations. While it introduces some complexity, the benefits of resilience and scalability make it an essential approach in modern data management. That wraps up our exploration of leaderless replication. We hope this discussion has clarified how databases manage concurrent operations and the significance of versioning. If you enjoyed this episode, please subscribe and leave us a review. Join us next time as we dive into more exciting topics in the world of technology. Until then, keep questioning and keep learning.